in GATE from matrices you will get every year at least one question, and sometimes you might get two questions, like a combination question, uh, some kind of questions from graphs like adjacency matrix, like that. Okay, so whatever it is, this topic is also important in terms of the number of questions we get in GATE, as well as it has applications in other subjects also, right? So what I'll do is, in this video, in the first video, I'll just present some basics. Even though you know them, I'll just try to just go through them very fast, so that the subject will be complete. Okay, so there are some matrices which are very important for some operations. So I'm listing down all those matrices here, and we shall go through them, and then we can get into the operations. Okay, so first of all, a matrix is nothing but it looks like a 2 by 2 array. In data structures we have already seen the 2 by 2 arrays, right? So rows and columns will be there. It is a kind of 2 by 2 array. And now the general way of representation is like this: we put some square braces and then we write m by n, where m represents the number of rows in the matrix and n represents the number of columns, right? So m means number of rows and n means the number of columns, right? And when m is not equal to n, then we call such a matrix as rectangular matrix, and when m equal to n, we call such a matrix as square matrix. For example, if I have any matrix like this, if I take any matrix like this, the number of rows in this is 2 and the number of columns in this is 3, right? And m is not equal to n, number of rows is not equal to number of columns. Such a matrix is called as rectangular matrix. Whenever m is not equal to n, it is called as rectangular matrix, and when m equal to n, that is called as square matrix, right? So if I write any matrix like this, right, such a matrix is called as a square matrix, 3 by 3. Got it? So what is the importance of this rectangular matrix and square matrix is, later when we are doing some operations like solving the equations, then I'll tell you it plays an important role to distinguish between these two. Okay, and the next type of matrix is unit matrix. So whenever you are trying to perform matrix multiplications, unit matrix is very important. So why is it called unit matrices? It is exactly same as the number 1 in the number system. For example, when you are talking about the natural numbers, the importance of 1 and the importance of unit matrix in the matrices, both are same. I mean, they can be thought of as logical equivalent. I'll show you why it is important, especially when we do matrix multiplication. Okay, so unit matrix is a square matrix. Square matrix means always the number of rows and number of columns should be equal in a unit matrix, and then the diagonal element, this is called as principal diagonal. Okay, so what is diagonal elements means, in order to understand diagonal elements, we can think of it this way. See, let us say this is a matrix A, and it is a 3 by 3 matrix, and it is having 9 elements, and now the location of the first element is 1 1, first row first column, and the location of the second element is 1 2, first row second column, and the location of the third element is 1 3, first row third column, right? And then the location of this element is 2 1, second row first column, 2 2, second row second column, 2 3, second row third column, and then third row first column, third row second column, third row third column. Got it? So when you have the elements like this, okay, now whenever you have row equal to column, this 1 1 2 2 3 3, when you see these are equal, right, we call those elements as principal diagonal elements. Got it? So in unit matrix, the principal diagonal elements will all be 1, and all the other elements which are other than this principal diagonal will be zeros. That is what we call as unit matrix, right? And the next one is null matrix. Null matrix means any matrix in which everything is 0 is null matrix. It need not be a square matrix. You can take any matrix. If all the elements of the matrix are called null or zeros, then it is called as null matrix. It is also sometimes called as zero matrix. Null matrix or zero matrix, both are same. And what is the importance of unit matrix is, it plays an important role in matrix multiplication, and null matrix means it plays an important role in matrix addition. Okay, I'll tell you, there are definitions which I'll tell you later. It is called as multiplicative identity and is called as additive identity. Okay, don't worry about it, we shall come to the topics. Okay, and the next type of matrices is row matrix. Row matrix means the entire matrix is completely one row, that is called as row matrix. So generally the normal representation of row matrix looks like this: 1 by n. 1 by n means 1 means only one row, and n means there are n elements in the row, got it, n columns. And column matrix. Column matrix means the entire matrix will consist of only one column, right? So the normal representation is like this: n by 1. N by 1 means one column, and n means n rows, right? So n by 1 means like this. And then the next one is submatrix. Any matrix obtained by omitting some of the rows and columns from a given matrix A is called submatrix. So why do you want to omit the rows and columns is, later I will show you. While we are trying to find out the matrix inverse, right? Matrix inverse means, okay, we shall go step by step. I'll tell you when that topic comes, but then here try to understand this operation. So what is a submatrix is when we omit either a row or column or both of them or any number of them, then we get something called as submatrix, right? It is just similar to that subgraph, if you remember. In subgraph also we omit some of the vertices or some of the edges or both of them, and then we get the submatrix, subgraph, right? Similarly here also we can do the same on the submatrix, right? So see this, I'll just take an example and explain. Let us say this is a matrix, right? And what is a submatrix is, one more thing, it itself, let us call it matrix A. A itself is a submatrix to A. A is a submatrix to itself, right? And moreover, if you try to eliminate either a row or a column, again you get the same matrix, again you get a submatrix, right? Which means you can delete this, then the remaining elements like this 2 3 5 6 8 9, this is a submatrix of A. Or you can eliminate this also and you can call the remaining, right, 5 6 8 9, this is also a submatrix. Or you can eliminate this row as well, which means this will be eliminated, and 8 9 is also a submatrix, got it? So you know, a submatrix is nothing but you eliminate either some rows or some columns or both rows and columns, and the resulting matrix, whatever you get, you can call it as the submatrix, right? And out of these submatrices there are some special matrices which are having some significance, right? So one such matrix is principal submatrix. See this, principal submatrix means, let us say we have a square matrix initially, 1 2 3 4 5 6 7 8 9, a square matrix. So from this square matrix you are supposed to find out a square submatrix in such a way that the resulting submatrix principal diagonal elements should also be the principal diagonal elements in the original matrix. Okay, what I mean to say is, see this. Now if you try to eliminate this particular row and this particular column, first row and first column, then what is the submatrix you get? 5 6 8 9. Therefore the resulting matrix is also a square matrix. First, the given matrix is a square matrix. Now if you observe this, these elements 5 6 and 8 9, now if you find out the principal diagonal, it is 5 9, isn't it? So these elements, these principal diagonal elements also happen to be present in the principal diagonal of the original matrix, right? So then such a submatrix is called as principal submatrix. So how do we get the principal submatrices? From a square matrix, if you eliminate the corresponding row as well as the corresponding column, which means if you are eliminating the first row, then you are supposed to eliminate the first column. If you eliminate it that way, then you are going to get a submatrix in which we get the principal submatrix, right? So let's do one more example. I want this point to be clear because it is very important later on. Let's eliminate second row and second column, right? Then see what is the submatrix we get, and then we shall see whether it is a principal submatrix or not. So this is the second row, right, and this is the second column. Now when we eliminate second row and second column, what is the submatrix that we get? The submatrix that we get is 1 3 7 9, right? Now this is a square submatrix. First of all, it has to be a square submatrix. And one more thing, from a square matrix, if you eliminate exactly one row and one column, the resulting submatrix is also going to be a square matrix. Which means why does it happen that way is, from a square matrix, which means we know number of rows and number of columns both are equal, m by m, right? And if you eliminate exactly one row and exactly one column, then the resulting matrix is going to be m minus 1 by m minus 1, isn't it? Because we have eliminated only one row and one column, and so the resulting matrix is also a square matrix, right? So always remember this, from a square matrix, if you eliminate one row and exactly one column, the resulting matrix is also going to be a square matrix. Fine. And now when is it going to be a principal submatrix is, after eliminating the row and column, you check the principal diagonal of the resulting matrix, the resulting submatrix. That one should also happen to be, the principal diagonal elements should also happen to fall in the principal diagonal of the original matrix, right? Then we can say that it is a principal submatrix. Now if you watch it, see, I have eliminated second row and second column. Then what did I get? 1 3 7 9. Now you check the principal diagonal elements of the resulting matrix. This is the principal diagonal elements, right? And 1 and 9, these two elements also happen to be the present in the principal diagonal of the original matrix. Then what can you say about this? It is the principal submatrix. Got it? And it is not always true that if you remove any row and any column randomly, we might get the submatrix, the principal submatrix. It is not true. Why is it so is, let's check this one. Instead of eliminating first row first column, second row second column, or third column, so one thing is for sure, if you eliminate first row first column, second row second column, third row third column, if you eliminate any of these like this, you are going to get principal submatrix. That is fine. But then any other combination of eliminations may not result in the principal submatrix, right? For example, let's eliminate first row and second column, which means let's eliminate first row and second column and then see what are the elements remaining. If you eliminate first row and the second column, the resulting elements are going to be 4 6 7 9, right? And now if you observe the principal diagonal, it is 4 and 9, but then 4 is not present in the principal diagonal. See, I am not talking about the particular element 4, I am talking about that position, right? Initially this is 2 1, right? And here it is 2 1, but 2 1 is not present, which means if the original matrix is containing the elements 1 1 2 2 3 3 4 4 something like this, then the resulting submatrix should also contain a part of these elements as the principal diagonal elements. Then only we can say that the resulting subgraph is principal submatrix. Okay, fine. So let's see some more properties on this, then we can look at the problems. Okay.